It looks like it's going farther away. What are you gonna do now, Gavin? Keep talking about it.
Christian's charging his tab.
It's okay if mine is charged, as long as Gavin's in charge.
Yeah, are you serious now? Wow.
Variation of
That's
not variation like at all.
All right. So let's talk about some stuffs real quick, right? My plan was for the IA to be your final exam as your final exam grade. I'd still like that to be the case. Originally, my plan was to have that due when we come back from Thanksgiving. Let's make it the Friday we come back from Thanksgiving, okay? But don't underestimate the amount of time it's going to take to do your typing and do your data stuff. I still want to leave a little bit of time for you to ask questions as you are working through your data processing stuff, but try to find a day during break to sit down and get your data set up, finish doing your calculations that we started typing in. Now that you have your actual numbers, so after listing the formula, show how you would plug your numbers in, do a ... and then we did that when we were typing, right? You guys remember?
Yeah.
Try to find a day, maybe this weekend while it's fresh and before the break kind of gets away from you.
So let's do the 1st of December.
That sounds right. That should give me enough time to get those graded. We are required also to do something on the exam day. This is what I would like to do, is I would like you to make a less than 3-minute video where you just talk about what you found, what you did and what your result was. And we're just going to watch those 3-minute videos as the exam day. So you can bring things to eat or drink. We're just going to watch the videos about what people did. I'd say 1 to 3 minutes would be the time frame you're looking for there. Not a long time. Talk briefly about what you did, what worked out, share some numbers, some statistics with us and what that meant. But that's all I really want for the exam day. Does that feel okay? Hopefully that's pretty low stress. Get this thing buttoned up out of the way even before the mad rush of end of the semester tests begin. But you're going to want to start typing sooner rather than later, right? Give yourself a chance to write a rough draft, let it sit there for a couple of days, come back and read it and make some edits. While you're writing, I would have this document on hand to reference. So this is the very first document in the IA piece. So it's tells you all the stuff you should talk about in your introduction. We've already written those, and ideally I wanted to read those and get you some feedback before, but I couldn't do it. But I should have them hand back from you when we get back. But it has what you should discuss in your information and data collection section, what you should talk about and have in your mathematical processes section. Notice that's a lot of stuff, right? What you should talk about in your reflection section. Yes.
So there's a page limit?
I don't think so. I don't think so. It's done when it's done. be thorough, but don't like overdo. There's no reason to pad, right? Be thorough, but don't pad, is what my advice to you would be. And then there's some discussion of like organization. And then this reminder about the video piece. Okay. Keep in mind, there are 2 ways to earn extra credit on this if you're looking for some extra credit to pad out what you're doing. So if all of your calculations are typed, nothing is handwritten, which should be the case for all of us because we spent a day in class kind of doing most of it or a lot of it. That's up to 5 points, depending on the quality of that quality of what you've done there. And then the other extra credit option is after you've done your correlation in your mathematical processes where you found your R, is to look at different possible relationships in your data based on your scatter plot. So whether it looks exponential or logarithmic or whatever, you want to discuss like why you think it looks like that, or what about the situation leads you to believe that like, oh, I would expect this to be, exponential. You should then find that new regression equation based on that form. You can use your calculator to do that. It's not required that you do it by hand, but you can discuss that like, I modeled this using my calculator. L1 and L2, and then do like, yeah, for sure, you can do that. Or you could use Excel, right? Like it doesn't need to be in your specific calculator because I know yours is not the easiest one to work with. But that's 2 extra credit options, right? So like, an extra pad of 10% if you do both of those things and do them well, right? But there's partial, again, both of these say partial is available. So even if you attempt it, and I find it a little lacking or whatever, and maybe you get 3 or 4 instead of 5, which is great, right? Like that's a nice cushion. Yeah. Luke.
So would the extra grade go into like our test category, or does it go into?
This is the exam grade. It's going to go onto the paper, so it'll go into the exam category. In the past, this has been a test grade. I'm going to count it as an exam grade this year because we can, and this is a lot, and I don't think you should have to take a final exam if you did all this work to do this thing. And I think you guys are probably on board with that.
If they try their best.
Well, so let's see, where's the thingamajigger that shows?
And then so we don't write them out.
Correct.
I know I really does Ivy work when you have to write it?
Some classes have the stuff done at the end.
So we are we gonna have
No.
No, because you have
The IB test?
You have the IB test.
No. Wait, that doesn't count against their actual
Is next
grade,
semester
right?
like not so much like statsy now? Is it more like?
Correct. The next semester's not so
Like, do I see some,
statsy.
like, extra numbers?
There's been lots of numbers this semester.
I know, but like I need like
Oh my goodness,
side
more like
notes.
an English
Where did that go? I thought I had one in here that on how this was graded.
I'd rather do that than
You're wild.
stats. No.
I hate it. Yeah, Mr. Fulk, I'm really just craving like a little foil problem. It's not gonna be a real
Why would we do it right?
I know.
I'm really creative. Just find X and that's all you have to do.
Okay. So if you look at this second document in the IA list, this has like the conversion from your IB score or your rubric score to your IB score to your test or to your score for the paper. So notice that like 0 to 2
Oh.
is 60. So like 9 to 11, 80. And they talk about this talks about the things that you're being graded on in there and like what these things mean. Where if you look at this thing, the IA criteria, they talk about, they have the different rubrics for each topic. Let me just find it real quick. So yeah, here's the 5 things that the IB is grading your paper on. So like presentation, this is the rubric for the presentation, right? Exploration is coherent, well organized, and concise. That's what the 4 looks like. And I think back on this paper, it talks about like what coherent means, what well organized, and what concise means, like what I would be looking for when I'm grading it. And if you look at the next one for the processes, or the communication, excuse me. So again, the max is looking, mathematical communication is relevant, appropriate, and consistent throughout. So what you're talking about is like notation and vocabulary, that you're using the correct vocabulary, you're using the correct notation. Yeah, so when you say, you know, like, you don't say the R value, you say the Pearson product moment correlation coefficient, and then put like parentheses R, so you've defined what R is before you start using it. So like that kind of stuff, you know, that like you don't write the chi-squared symbol without first telling us that what chi-squared is. Things like that, or, you know,
Yeah.
that you're using notation when appropriate, but not using it before you defined it, kind of thing. Those are, and again, like if you go back and you look at this one, so relevant, meaning that notation, symbols, and terminology are appropriate and well defined. Representation, multiple forms of representation are present, graphs, equations, etc. We're doing a scatter plot, you're doing a best fit equation, so like assuming you actually do those things, like you should hit that. Consistent, all math, notation, and terminology are used in the same manner throughout. Note that this means something can be used incorrectly, but still consistently. So again, like if you say R, you know, like that may be like, you know, incorrect, but you did it every single time, so you can hit the consistent part, even if, right, like even if you don't have like the relevant part where you've inappropriately used a symbol, but it's been like the consistent symbol throughout. Diego?
So for things, should we be like overly explaining them? Like, or should we assume that, okay, so like take your standard deviation. Should I explain what that like signifies and also how I found them?
You can use the textbook's definition, like, quote, we calculate standard deviation, which is as defined in, you know, like the name of the textbook or whatever, like cite the textbook, and you can quote the exact definition from the textbook with a citation.
Okay.
You know, this, and then say in your own words, this is essentially like the average difference of a random data point from the mean, right? Like, and you can say that and then move on, you know, or then let's say like, this is a measure of dispersion for my data. So like how spread out my data is. And you can comment that maybe like, oh, my standard deviation was really small here, so it probably means this data, you know, should imply this data is pretty well clumped together, which is good, right? That's what.
After you say like your son or whatever, like once you have to keep saying it every time you say R value.
I'm sorry, what?
For the consistency, because the R value is the Pearson product.
Right.
Do you say that every time instead of R value, or can you say R value?
If you say we're going to calculate the Pearson product moment correlation coefficient, which we'll represent with the symbol R, every time you reference that, you can say R, right? Like the first time you say it, give the full name and full definition and what it means, and then the symbol you're going to use, and then you can symbol throughout, right? You just have to be careful that the first time you're using it, you have to define what these things are, right? Like you don't want to say, you know, the standard deviation of my independent variable before you say sigma x, right? Like you have to be careful about that kind of thing. Like that's what we mean, you know? You know, and then like personal engagement, where is this going to be present? Probably in the introduction and conclusion, right? Like notice that was part of the introduction when we talked about it. Was I wanted that. And there's two pieces. There's significant and outstanding. So, blah, blah, blah. Reflection, again, the end of your paper. If we go back and look at these things, like, those are the key, like, terms in here. So, like, personal engagement. Outstanding personal engagement versus significant. You know, like, and then on that paper we defined what like significant and outstanding meant. So this is like what I'm going to be reading, looking at when I'm grading your papers are these rubrics. And then I kind of explain on this document like what the verbiage means, like what I'm going to be looking for. You know, like when the reflection, what does limited versus meaningful versus substantial versus critical really, what does that mean for me as I'm reading it and grading it? Yes, sir. If you have enough data so that you're past the large counts condition for your chi-square test, there's no reason to collect more data than you have. If you pass the large counts condition for your chi-square test, there's no reason to collect more data. Luke.
Where are we like content-wise for this next one? Are we like not IA related? We're talking just chapter book.
Yeah, so on the syllabus, the plan was to cover chapters 1, 7, 13, 14, 8, and 12. We are ready to start 8 today. That's what we'll be doing when we get back from break as well. And I think we can probably finish 12 if we're not having a final exam. So we don't have to like stop and do review stuff.
Are we gonna have 8? We're gonna have a test on 8.
For sure a test on 8. Probably, maybe.
So don't these two alternative R chapters are easy?
Rank them compared to what we've done.
No more difficult than the hardest things we've done so far. I don't know, but I don't think any of it's been particularly hard. Some of it's been fast, which is the hard part, but none of these things are like, oh, that was like a page of calculations and all this symbol pushing going on. It's all been like some definition that we need to know and some calculator literacy.
That's just this semester, right?
Correct.
So we only have one more chapter.
One more chapter. All right.
Alexis said this.
So I'd like to now take some time and start on 4.1. Okie doke.
Yep.
Does that feel, you guys feel okay about IA stuff as we're getting closer? Okay. Again, if I were in your shoes, I would try to have a rough draft done by the time we get back, in case that week we get back is crazy, to where it's like, okay, I can have enough time to proofread and like do some edits, but I might take a day and sit down and during break and just try to write the thing in a day.
It's so bad.
All right. So we're going to be talking about probability in section 7 and 8, or I'm sorry, 8 and 9 or whatever, 8 and 12. Maybe that was the two chapters. Anyways, probability. So what are we talking about with probability? The chance of something happening, basically a percentage, right? So we start with something called the law of large numbers, which says that if we observe more and more repetitions of a chance process, the proportion of times that a specific outcome occurs approaches a single value. Essentially, that your experimental probability approaches your theoretical probability as the number of samples moves to infinity. So like if we flip a coin 10 times, we get some probability. If we flip a coin 100 times, we get a different probability. If we flip it 10,000 times, we get a different probability. As the number of coin flips goes up, I'd expect that probability to be approaching 0.5. Why 0.5? That's the theoretical probability for a coin flip. Thank you. Luke. So this is like a simulation of like, okay, we flipped a coin. One time, the probability of getting heads was 100%. And then 2 times, I got a head and a tail. And then I got a head, 2 heads and 1 tail. And then a second tail. And it's just like bouncing around here. And as I toss this coin like many, many times, it looks like that probability is settling down to right around 50%, right? That's kind of what we're saying. Feel okay? Keep in mind that the probability for any outcome is a number between 0 and 1, between 0% and 100%, right? Can't have negative probabilities. You can't have probabilities greater than 1. Okay. Misconceptions about randomness and probability. The myth of a short-run regularity. The idea of a probability is that randomness is predictable in the long run. Our intuition tries to tell us random phenomena should also be predictable in the short run. Probability does not allow us to make such short-run predictions. So for example, we're gambling on coin flips. The last 4 coin flips has come up heads. You think to yourself, well, the next one must be tails. It's too many heads in a row. What's the probability of getting tails on the next coin flip? Still 50%. It doesn't matter. You've just kind of convinced yourself that like tails should come up, has to come up soon because we've had so many heads in a row. No. Still the same. Is that okay? All right. The other one is called the law of averages. So this is also a myth. Probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. Same idea, right? Coin flips. These previous coin flips aren't going to affect future coin flips. Doesn't work like that. What may happen, though, is like a regression to the mean. Meaning that, like if the probability of should be 50%, and the last 10 coin flips, the probability has been more like 70%, I'd expect over the long term, you know, like that probability to drop back down towards 50% again, right? It's kind of like, you know, like you're a baseball player and you hit like 600 for the first week of the season, but you've been a 250 hitter your whole career. Probably going to end up still a 250 hitter. You're just going to, like, you know, slowly peter off. All right. Probability models. So to properly discuss the probability of events, we first have to figure out how many different events can occur. The hardest part about probability is the counting. Like how many different ways can something happen, and how many ways can the thing we want to have happen happen. So we call an outcome the result of a trial, and we call the sample space the set of all possible outcomes. So for example, if we're talking about flipping a coin, what are the outcomes? Heads or tails. What's the sample space? Sample space contains two outcomes, heads and tails. Now, if I flip a coin twice, what are the outcomes? You could get two heads, get one head, one tail, and get two tails, right? There's three outcomes if we flip a coin twice. How many things are in the sample space? There are four. Because there's two ways to get heads, tails. You get heads first, tails second, tails first, heads second, right? Now that's still the same outcome, but there's two different ways to get it. Does that feel okay? All right, so for a probability model, we want to describe some chance process that consists of two parts, a sample space and a probability for each outcome. So list the probability model for rolling two fair dice. How many sides are on a dice?
6.
So if you roll two at the same time, how many different outcomes can you get?
30.
That,
Yeah.
right? 36 outcomes. Everybody's okay? Each of these outcomes is equally likely. However, what if we say, what's the probability of rolling a 7? How many outcomes give us a 7? 2, 3, 4, 5, 6. So 6 out of 36 would be the probability of rolling a 7, because there's 7 outcomes that have a roll of 7. Or 6 outcomes that have a roll of 7. Jeepers. Okay? Just as an FYI, when you're building out your sample space, it's best to try to do this systematically, like we've done here. You know, like the first row is where the first dice is fixed to 1. The second row is where the second dice is fixed to 2, right? It just makes it easier than like randomly writing stuff down. Okay. An event is a collection of outcomes from some sample chance or from some chance process. So rolling a 7 is an event that consisted of 6 outcomes in a sample space of 36 outcomes. How many events are there in rolling 2 dice? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 11 things, right? Unless you want to include a specific roll, as in how many different ways are there to roll snake eyes? 1. How many ways to roll 2 6s? or 2 3s, right? Those are different rolls, right? Or how many ways are there to roll doubles? If you're playing Monopoly and you get to go twice if you roll a double. 6, right? So like though an event could be anything. Is that okay? Typically, that event we note with some capital letters like A, B, C, etc. So if A is an event, we say the probability is P of A. So let's take that dice rolling example and say the event is the sum is 5. How many different ways do we have to roll a 5? 4, right? That diagonal right there. Everybody cool? Okay. What if we did the sum is not 5?
32.
How'd you get that? 4 out of 36 minus, or 36 out of 36 minus 4 out of 36, right? Excellent. This idea of taking 1 minus an event is called a complement. So the complement of rolling a 5 is not rolling a 5, which would be 1 minus the probability of A. Everybody's okay with that? So some set notation symbols that we need to be familiar with. So the curly brackets indicate that the things listed are members of a set. N of a set tells us the number of elements contained in the set. Alternate notations that the IB doesn't use, but you would see in a future math class, would be like the absolute value bars around a set. Would also be indicator for the number of things in a set. We use the capital letter U as the universal set, so that's the entire population being considered. The circle with a line through it is called the empty set. That's a set containing no elements. This symbol is the symbol for element. So if we say like X is an element of A, so like the dice roll of 1, 5 is an element in all the dice rolls for 2, right? Or in that sample space. If we put a slash through it, that's not an element. This dome is the intersection symbol. That's the set of elements that are in common between 2 sets. And the union symbol is the set of elements that are in either A or B. That is, they are the elements in set A, in set B, and in the intersection, right? So it's anything that's in both of them. And then this symbol is the subset symbol. If you put a little bar underneath it, it means subset or equal to. So if I said like A is a subset of B, with the bar, it means that A could just be all of B. If it doesn't have the little bar underneath it, it means it is a proper subset, so it would not be B. It has to be something that's strictly contained in it. So let's look at some examples here. So we have some set A, some universal set, which is represented by the square. The set A represented as a circle. So A is the stuff inside the circle, and the complement of A is all the stuff not in the circle. Everybody's okay with that? Which is the same thing as the universal set minus the stuff in A. We say that 2 events A and B are mutually exclusive, or sometimes they'll use the term disjoint, if they don't overlap, i.e. they have no outcomes in common, i.e. their intersection is empty. So for example, sets A and B here are mutually exclusive because they contain no overlap. There's no things in common between them. So an example of 2 mutually exclusive sets. Consider the sample space for flipping a coin once, or flipping a coin, one coin, and the sample space for flipping or for rolling 2 dice. Those are mutually exclusive because the outcomes are not in common, right? The coin flip are heads and tails. The dice rolls are like, 1 and 5 or that kind of, right? So the intersection of 2 sets, A and B, is the set of outcomes in both A and B. So for example, if we had A was rolling a 6 and B was doubles, what would be in the intersection of those two? Rolling 3-3, right? Because that's both rolling a 6 and a double. Everybody okay with that? So like 3-3 would live here, but like 1-1, 2-2, 4-4, 5-5, 6-6 all lives over here. And then like 1-5, 2-4, 4-2, yada yada, live over here. The union is all of the events that are in A or B. So everything in A, everything in B, everything in the intersection of the two. So if we use the same example, if A is rolls of 6 and B is doubles, how many outcomes do we have in A union B? 1-5, 2-4, 3-3, 4-2, 5-1, 1-1, 2-2. We already counted 3-3, 4-4, 5-5, 6-6. I count 10 outcomes. Is everybody okay there? Have to be careful not to count the things in the intersection twice. And then your hint is U for union and this N for intersection. I don't know if that helps or not. Okay, let's look at some examples here. Flip a coin twice and record the results. Represent the sample space in list form. So what would our sample space be? Head, 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 tail, tail, head, tail, tail. Right? There's our sample space. Those are all the possible outcomes. Then we just need to add them into set notation. What is that going to mean? I put a curly bracket around the list and commas in between them. And write it with a U or an S, capital S for sample space, or U for universal set. Either would be appropriate. Now, if we want to change this set into a probability model, we want to represent the sample space in tabular form. So there would be our table. Notice, what is the difference between this and what we just wrote?
It's the same.
Yeah, it's like the same thing. It just listed as a table, right? Here's head, head. Here's head, tail. Here's tail, head. Here's tail, tail. Right? Nothing confusing. As a tree diagram, what would that look like? So my first decision could be head or tail, and my second flip would be head or tail, right? Oh my goodness, there it goes. So head and tail, and then head and tail. So if I look, here's my head, head. Here's my head, tail. Here's my tail, head. Here's my tail, tail. Is everybody okay with how I did that? Still represents the same information, right? How about as a Venn diagram? There's no overlap, right? Because each one of these is like their own thing. How about into a probability table? So the first toss has two possibilities, the second toss has two possibilities, and we just turn it into a table. Notice that first toss, we've listed those as the X value, and the second toss we've listed as the Y value. All right, let's look at some events and operations. So again, rolling a standard six-sided die, just one of them. Event A is observe an odd number. How many outcomes in this event? 3. What would they be? 1, 3, 5. Easy enough. Okay, when rolling a standard six-sided die, what is our event B is observe a number less than 5. How many outcomes do we have there? 4, right? 1, 2, 3, and 4. Okay. How about if we look at the intersection of A and B? Should contain 1 and 3, right? Everybody's good there? Easy enough. How about not A? Right? That's the complement symbol. That's not A. 2, 4, and 6 is correct. How about A union not B? So not B would be 5 and 6. A union B then would be 1, 3, 5, and 6.
No, I won't. I realize that seems
Is that okay? Fine point here. Shh. Notice that 5 occurs in both A and not B. When I write the union of these, 5 is only listed once. Sets have no repeating elements. If you list 5 twice, it is wrong. Got it? Okay. Using words, interpret event B. These would be you observe an odd number, or you observe a number less or greater than or equal to 5. Or not less than 5. Greater than or equal to is the same as not less than, right? What is the intersection of A and B, where A is universal and B is empty? It's the empty set. Oh, what are they doing here? What are we doing here? Oh, okay. I'm sorry. These are just like properties. U is the universal, and this is the empty set. This is just, okay. So intersection is commutative. Union is commutative. Complement of a complement is the normal. Intersection with a set and the universal set is just the set. The union of a set and the universal is the universal. Intersection of a set and its complement is empty. The intersection of a set and its complement is everything, universal. And then we'll pick up where we left off after we get back from vacation. Work on your IAs. That's your homework. Do we have a problem set this week?